ownership and borrowing in depth. If you've tried to learn Rust and hit a wall, it was probably the borrow checker. Every Rust developer does. But here's the thing. The borrow checker isn't telling you that your code is complicated. It's telling you that your code has a bug, and it's showing you exactly where. In this video, we're doing ownership and borrowing in depth. Move semantics, borrowing rules, slices, lifetimes, and the patterns that make this click. Chapter 1. Stack versus heap. What ownership is really about. Stack allocations are trivial. The compiler calculates the total size at compile time. Heap allocations are different. The runtime calls the allocator, which returns a pointer. Rust needs to know when to free heap memory. Without a garbage collector, it does this through ownership. When the owner goes out of scope, Rust drops the value automatically. One owner, one cleanup. Chapter 2. Ownership rules. 3 rules define the entire model. 1. Every value has exactly one owner. 2. There can only be one owner at a time. 3. When the owner goes out of scope, the value is dropped. Let S equals string from hello. When S goes out of scope, string drop is called. The heap is freed. No leak, no double free, no dangling pointer. Chapter 3. Move semantics. Let S1 equals string from hello. Let S2 equals S1. S1's ownership moves to S2. The stack data, pointer, length, and capacity is copied, but ownership transfers. S1 is invalidated. If both owned the same heap address, both would try to free it. Double free. Undefined behavior. Move semantics prevent this. Only S2 is responsible. Chapter 4. Copy types versus move types. The copy trait marks types that are trivially copyable by value: integers, floats, booleans, characters, and tuples of copy types. Assignment copies them. For everything else, string, vec, box, assignment moves. The rule: if a type could be expensive to copy, Rust forces you to be explicit by calling .clone. This makes the allocation cost visible in the code. Chapter 5. Ownership through functions. Passing a value to a function follows the same rules as assignment. Move types are moved into the function. After the call, the caller can no longer use the variable. Copy types are copied. This is why most Rust functions accept references rather than owned values. Borrowing lets the caller keep the value. Chapter 6. Return values and ownership. Return values transfer ownership to the caller. Create a string in a function, return it, the caller becomes the owner. Passing a value in and returning it back works, but it is tedious. The real solution for passing data without transferring ownership is references. Next chapter. Chapter 7. Shared references. Ampersand T. The ampersand operator creates a reference. A reference borrows the value. It doesn't own it. When the reference goes out of scope, the referent is not dropped. You can have any number of shared ampersand T references simultaneously, as long as no one is mutating it. Fn, calculate length, taking s, colon, ampersand string, arrow, u size.
Chapter 8.
Mutable references, ampersand, mut-t. Mutable references are written, ampersand, mut-t. To create one, the original binding must be mut, and you pass ampersand mut explicitly. Only one mutable reference may exist at a time. No shared references may coexist with a mutable one. This single rule prevents data races at compile time.
Chapter 9.
The borrow checker rules. At any point in time, for a given value, you may have any number of shared immutable references, or exactly one exclusive mutable reference, but never both simultaneously. All references must be valid. These two rules implement a compile-time read-write lock, either many readers or one writer. Never both.
Chapter 10.
Non-Lexical Lifetimes. Non-lexical lifetimes, introduced in Rust 2018, make the borrow checker smarter. A borrow is considered alive only until its last use in the code, not until the end of the scope. This means you can take a mutable borrow after shared borrows have been used for the last time. Code that feels like it should work now does.
Chapter 11.
Dangling references, the compile error. In C++, returning a reference to a local variable is undefined behavior. It compiles without error, but crashes at runtime. In Rust, it's a compile error. The borrow checker sees that the reference would outlive the data and refuses to compile. The fix: return an owned value and let the caller take ownership.
Chapter 12.
String slices. Ampersand str. Ampersand str is a string slice, a fat pointer containing a pointer into string data and a length. No ownership, just a view. String literals are ampersand str, pointing to read-only binary data. Prefer ampersand str over ampersand string in function parameters. It's more flexible, with the same performance.
Chapter 13.
Array and vector slices. Ampersand bracket t bracket is a slice of any contiguous sequence. Like ampersand str, it's a fat pointer to the first element and a length. Using ampersand bracket t bracket in function signatures rather than ampersand vec_t is idiomatic because it accepts arrays, vectors, and sub-slices.
Chapter 14.
Lifetime annotations. When and why. Lifetime annotations are a communication tool. The tick A syntax is just a name, meaning some lifetime. When you write ampersand tick A str on both inputs and the output, you're saying the output lives at most as long as both inputs. The compiler verifies every call site satisfies this constraint.
Chapter 15.
Lifetime elision rules. 3 rules let the compiler infer lifetimes. Rule 1. Each input reference gets its own lifetime. Rule 2. If there's exactly one input reference lifetime, the output borrows from it. Rule 3. If there's an ampersand self parameter, the output borrows from self. Explicit annotations are only needed when the pattern is ambiguous.
Chapter 16.
Common ownership patterns. The most ergonomic pattern: functions accept references when reading, return owned values when producing, and structs own their data. When you need shared ownership, RC of T gives reference-counted, single-threaded sharing, and arc of T gives thread-safe sharing.
Chapter 17.
Interior mutability. RefCell and Cell. Sometimes you need to mutate data through a shared reference. Cell is for copy types, simple get and set. RefCell enforces borrow rules at runtime rather than compile time. It panics if you take two mutable borrows. RC of RefCell of T is the pattern for shared mutable ownership in single-threaded code. Arc of mutex of T is the multi-threaded equivalent.
Chapter 18.
Summary and what to learn next. That's the ownership model, start to finish. This is the hardest concept in Rust, and you've just worked through it in depth. Everything else in the language builds on this foundation. What to study next? Structs and enums, then the trait system. Once you can define your own types and implement traits on them, Rust's design patterns open up completely.
If this helped,
Subscribe. Next video is structs, enums, and pattern matching in depth. Leave a comment if you hit a specific borrow checker error you want me to explain.